Good morning everyone and welcome to today's worked exam answer video. Today I'm having a look at a question all about different organic mechanisms, but the way this question is presented is a little bit different from the questions that I've done with regards to mechanisms before, and that's because AQA in the 2023 exam decided to switch up the way in which they asked about different mechanisms. So rather than it being a name and outline a mechanism for this particular process or these two things reacting together to form a certain type of product, they wanted to test the information in a slightly different way. So they've drawn some of the intermediate species in these first two questions, and then on the third example on the back they've drawn the reactant species. And they're asking us to think about curly arrows, lone pairs and charges on intermediates, as well as potentially drawing the starting materials and in some places naming the mechanism. So let's dive into this and see how it's different, but also have a think about how we can still use all of that information that we will have learnt about different mechanisms to approach the question. So I'll start with part A, obviously. So it says figure 1 shows an intermediate, which just means it's not the final product, it's something that's formed in between the starting materials and the product. The intermediate doesn't last very long because there's then further changes that happen in another step. So figure 1 shows an intermediate formed in the first step of a nucleophilic addition-elimination mechanism. So the intermediate is what we have after the addition, and then in this step we'd be thinking about the elimination. Makes sense. Complete figure 1 to show the structure of the two reactant species with curly arrows and relative lone pairs of electrons involved in the formation of the intermediate. So things that have always been important in mechanisms, but they're just specifying we need curly arrows, we need relevant lone pairs when we're thinking about the formation of the intermediate. Then we also need to draw curly arrows and relevant lone pairs of electrons on the intermediate to show how the final products are formed. Doesn't want you to draw the final products, just to show from the intermediate how we would get to the product. So this is where we probably want to have a good understanding of nucleophilic addition-elimination to appreciate that that mechanism is only ever one that we would be asked to draw if our starting point was an acyl chloride, reacting, of course, with a nucleophile. In order to figure out what nucleophile it is, we can use the intermediate, and again, this is where we need to know the mechanisms fairly well to go, right, well, in this intermediate, this at the bottom here will have originally been our nucleophile that's then been added on to what was the acyl chloride to give us this structure. We can also use the intermediate to figure out exactly which acyl chloride it was, because we can use this alkyl chain to work out that it was propanoyl chloride. So an acyl chloride has the functional group C, double bond O, and then Cl. You could have a very similar looking reaction with an acid anhydride and a nucleophile, but we would only be writing acylation equations for those processes. We wouldn't be drawing nucleophilic addition-elimination mechanisms, so it has to be an acyl chloride. So what I'm then going to draw is, first of all, the two reactant species. So I'm going to draw my acyl chloride, CH3, CH2, C double bond O, Cl. And then my nucleophile is going to be methanol. So CH3OH. And that can act as a nucleophile because the oxygen of the OH group has a lone pair. So it says draw all relevant lone pairs, which we would always be doing in mechanism steps anyway. So I'll pop the lone pair on there. And then because they've told us it's nucleophilic addition-elimination, that then guides us in how we're going to go from those two reactant species to the intermediate, because we want to be adding in the beginning. And the biggest mistake that students make with this mechanism is they will draw their curly arrow from the oxygen's lone pair to the carbon, but then they'll want to immediately kick off the chlorine, which technically looks like addition and then elimination, but because it's happening in the same step, it's probably going to be more like substitution. So that's not what we've got to do here. The only way we can add the nucleophile on without breaking a bond that's going to cause an atom or a series of atoms to leave is to open up the carbon-oxygen double bond. And that's what we can see here. The carbon to oxygen is now a single bond. The oxygen gained both of electrons from that bond, gives it a negative charge. This oxygen from the nucleophile is forming a dative covalent bond with the carbon. It's using a lone pair in that bond, which it doesn't want to be doing. It doesn't have sole control of that lone pair anymore, so that oxygen will have a positive charge. Those are my reactants. That will then give me this intermediate, and on this intermediate we have to draw curly arrows and relevant lone pairs of electrons to show how the final products are formed. So this is where our elimination comes in. So that oxygen there has a lone pair, and that enables it to reform the double bond. So that's another thing that is quite helpful that we know about nucleophilic addition elimination as a mechanism. The products all still contain a C double bond O. What we're doing is changing what is next to the C double bond O from the Cl, as it is in an acyl chloride, to either an ester or an amide or an unsubstituted amide. So yeah, that helps us to then think about the fact that it's going to be the chlorine that is eliminated, so that we then have the C double bond O, which will then be next to this C and O. So this is going to give us an ester, but we can't have the oxygen bonded to three things. So to give the oxygen back its lone pair, the bond between the oxygen and the hydrogen will break and those electrons will go to the oxygen. This H will leave as a H plus, this Cl will leave as a Cl minus. That's where the HCl second product comes from. So bit of a different way of thinking about the mechanism, but obviously we still need to use all of our knowledge of what homologous series we start with for nucleophilic addition elimination, what's happening in the first step, what's happening in the second step, what do we mean by addition, what do we mean by elimination, what do we mean by nucleophile, you know, knowing where our lone pairs go and all of those sorts of things. But hopefully, having had a look at that, you can see how I've derived that answer. Next example says that figure 2 shows an intermediate, again, formed in the first step of a reaction mechanism of methylbenzene. So it's told us in this instance that we're starting with methylbenzene, so benzene being the 6-membered carbon ring where every carbon only has one hydrogen initially, and we've got the delocalized ring in the middle. Methylbenzene, one of those 6 hydrogens has been swapped for a methyl, so we then have 5 hydrogens and a methyl. So again, we have to complete figure 2 to show the reactant species and any curly arrows involved in the formation of the intermediate. We then have to draw a curly arrow on the intermediate to show how the product is formed, and then we have to give the name of the reaction mechanism, and that's going to give us our 4 marks here. So we know, because the question has told us, that we're starting with methylbenzene. So let's draw that initially. So benzene is our hexagon-shaped compound with our ring of delocalized electrons on the inside. They've put the methyl up top, so I will again follow suit. In terms of the other reactant species, we're going to need an electrophile. And how do I know we're going to need an electrophile? Well, a nucleophile that we used in the previous question is an electron pair donor. We're not going to have a nucleophile being able to attack a benzene ring because the benzene ring isn't going to want to take even more electrons from a nucleophile. Yeah, electrons don't want to move towards where there's lots of other electrons, whereas what we would want instead is for the benzenes delocalized electrons to be able to attack something that is electron deficient and can accept a pair of electrons, and that's what an electrophile is. So in terms of naming the reaction mechanism, if you're ever stuck between is it nucleophilic, is it electrophilic, think about those definitions. We're not going to be adding a nucleophile here because we're not going to have electrons wanting to attack other electrons. So name of the mechanism is going to be electrophilic something, and I'll come back to that in a second. And the electrophile, we can see, based on the intermediate, is NO2, which will have had a positive charge before it got joined on to the ring, and that would suggest it's electron deficient and is able to accept a pair of electrons from the benzene ring. So in terms of the curly arrow involved in the formation of the intermediate, from there to the nitrogen with the positive charge. When we do that, we use some of benzene's delocalized ring, so we then end up drawing it as this horseshoe shape with a positive charge on the inside, because again it's got fewer electrons in there than it did before it attacked the electrophile. We can then see that the NO2, they've decided to put it on this bottom carbon here. Now the thing that people can forget with benzene is the presence of one hydrogen per atom, with the exception of the top one, because it's skeletal formula for the benzene ring itself, but there is a hydrogen there. Benzene doesn't want to break open its ring of delocalized electrons because that brings it a lot of stability. So what we want to do is replenish the electrons in the ring, and we're going to do that by getting rid of the hydrogen that was on the benzene ring, which now needs to leave as a H+, and in doing that we reform the benzene ring. We get a H+ coming off, and fundamentally we've done a substitution reaction. Benzene won't undergo addition reactions because that would permanently break open the ring of delocalized electrons. Benzene doesn't want to do that. So even though in the intermediate we have broken the ring of delocalized electrons, we can reform it if we undergo a substitution reaction. So this is electrophilic substitution. And it's very easy to say electrophilic addition because we can't see that there is a hydrogen already there on the bottom carbon, but there is. Benzene is C6H6, methylbenzene C6H5, CH3. So that covers everything that we need. We've got two reactant species, we've got curly arrow there, we've got the curly arrow on the intermediate, we've named the reaction mechanism. Okay, so we've already had two different mechanisms from different parts of the specification. We've now got a third. If I turn over. So here is the final question. 12 marks in total for this question. So if you didn't know your mechanisms very well, you're probably going to shoot yourself in the foot here. Bit different this time because figure 3 is showing us the reactant species involved in the first step of a mechanism. They've also used skeletal formula there. We have to complete figure 3 to show the structure of the intermediate formed with curly arrows involved in its formation. And then again, we have to give the name of the reaction mechanism. Now, in terms of the reaction mechanism, they've given us a big clue because we've got a H- with a lone pair drawn on it. That would suggest that that is going to act as a nucleophile, so it's going to be a nucleophilic reaction of some kind. The other clue is that we're starting with a ketone, we're starting with propanone. When we're thinking about ketones, the only thing that ketones can turn into is secondary alcohols. We can reduce them back to the secondary alcohol that they were made from in the first place via oxidation. So because we have the C double bond O present, we've got a nucleophile in the H-, we are going to be thinking nucleophilic. It's not going to be substitution because we're not wanting to get rid of the C-O bond completely. We're going to break it down into a single bond, but unlike addition elimination where we reform that bond, we don't want to reform that bond now. So we are just going to be doing a nucleophilic addition without then getting rid of anything. But the first step of nucleophilic addition and nucleophilic addition elimination are exactly the same. The only difference is that we then eliminate in the second step. In addition elimination, we don't eliminate here. We don't need to show the second step because we've only got to show the structure of the intermediate formed and draw the curly arrows involved in its formation. So a nucleophile will always attack something that is delta positive, which is going to be the carbon of the C double bond O. Don't need to put your partial charges on, but the carbon will be delta positive and the oxygen will be delta negative. So the lone pair on the hydride ion, H minus, will attack that carbon there, and that will cause the C double bond O to break, become a C single bond O, and both of the electrons in the bond that is broken will go to the oxygen. That is going to give me, and I'm going to have to follow suit and go with a skeletal formula, which is going to be weird because I'm not going to be able to show that the hydrogen nucleophile is now added, but anyway. So we've got CH3, then the C where the oxygen is, and then CH3, and then we're going to have a hydrogen on there. We're now also going to have single bond to the oxygen, and then that oxygen will have a negative charge and a lone pair. The hydrogen is on this carbon, but we wouldn't be showing that in skeletal. Then what would happen is the O's lone pair would attack a H+, and that would then give us our secondary alcohol. We don't need to do that part, we just need to complete figure 3 to show the structure of the intermediate, formed with curly arrows involved in its formation. So we've got 1 curly arrow, 2 curly arrows, 3 for the intermediate, 4 for the name of that mechanism. So 2 reactions from sort of the carbonyls base chemistry. This one is from aldehydes and ketones. The first one was from carboxylic acids and their derivatives. And then we've got this mechanism from our aromatic topic. If anyone has any questions on how to answer that, please, as always, just let me know. Leave a comment on the video or drop me a message, or you can send me an email as well. But please do make sure you reach out because I'm here to help in any way that I can. Thank you so much for watching, guys, and for all of your support on my videos. I hope you have a really lovely day and rest of your week. Thank you.